1 to group 4?
The amino group. Atom with a lone pair. Group 1, yeah?
Yeah.
What type of director is this?
Ortho-para director?
Ortho-para director. Okay? Ortho or para. Para position's blocked. Usually you're not going to put anything there. There's some special reactions where you could end up with 2 things here. It's no longer going to be aromatic. Or maybe you could lose this group. That's unique. For us, we're typically not going to see it. There may be a question in the workbook where you some unique mechanism. First thing is we just say it's blocked. Ortho. What type of director do we have here?
Group 4?
Group 4.
Group 4, sulfur, electron poor, no lone pair. How does it direct?
Meta direct?
Meta, so where does it direct?
Right there.
Right there.
Same position. Reinforced, they both direct here. And that's why when we do that lab, we got the halogens ortho to the amine. You can put one, but then you can turn around and repeat, and the other one goes at the other position, which is also ortho and meta to the groups. So you would predict you're going to get reactions here and not over here, because this is meta to this and ortho pair or ortho to that, and that's not how these groups direct. Okay? Now, understanding why they do this, that's your resonance structures and stuff there. You need to understand the why. And so that's sulfonilamide. Okay, let's pick up there. Any questions? Metal reduction, reducing nitro group today? Nitrofluorine? Okay, I pretty much want to say that we should only do zinc. Some of you may have already written tin. It's just a small change. Tin, and instead of using HCl, we're going to use ammonium chloride. The tin reaction, the filtration is just so tedious and difficult. Zinc filter is much better. So everybody should do zinc. All right. Any questions about the lab? Good to go? Question?
In one part of the handbook, you said to keep 15 to 20 milligrams for terpene, and another part you said 5 milligrams. I was wondering which one you prefer.
Okay, that should be consistent. I'll try to either. What do you need? You need enough to maybe if I need to check an IR or something, or you need to turn this some in so I see that you have made compounds. You don't have to measure it. Ultimately, you're just going to turn in what you didn't use, but you need to leave some. Yes, everything you don't use, you need to turn in, and it needs to be some. If the vial is completely empty, it ain't 5 or 15. Okay. So, I gave you 4 groups. As I mentioned, some textbooks do it a little bit differently. This came out of some other textbook, perhaps the Smith textbook that we used to use. And they're giving you like strong, moderate, weak, where I just kind of gave you strong and weak. All right? You don't need to worry about this. They're all, okay, here. This is my grouping. I call both of these group 1. And then the weakly activating is my group 2. So I didn't differentiate between here. All these up here are going to be an atom with a lone pair. Okay? This is bonded to the ring. Every atom bonded to the ring has a lone pair and it's not halogen. So that's group 1 for me. All right? We can add. Why is these moderate with these strong? We can look at that. This is bonded to the aromatic ring, okay? OH versus O, like maybe ester. Atom and lone pair, both group 1. But this is actually more activating, okay? The OH is strongly activating, while the O carbonyl is only moderate. Why is this less activating than this?
Is it because the carbonyl next one?
Well, yes. Explain why though.
It's withdrawing from the oxygen.
Because this electrons are pumping into the ring here. You can do resonance. You can do resonance. Yes, you can do it here. But these electrons are also being pulled the other way by resonance. And you can draw a resonance structure putting these electrons here. So these electrons can't pump as much into the ring because they're being pulled the other way. And so this group is not as strongly activating as that. All right? And so, but it is still, okay, for me, I still call it group 1. But you should be able to sort of rationalize that of why these two are not as activating. Another important thing here is look at the amino groups. The amino groups, yeah. Well, what is this down here? Strongly deactivated. This is NH2. Well, what about the NH3 group, which would be positive?
It doesn't have any electrons to do resonance.
If you protonate it, it no longer has a lone pair. It's now an electron poor atom with no lone pair. This is group 1, strongly activating, but this is group 4, strongly deactivating. Ortho pair director, that would be a meta director. Because plus charge here, you can stabilize it by resonance. You don't want plus charge falling here, because then you're going to have two positives next to each other. And the way to avoid plus charge is to do a meta reaction. So it's also a meta director. Deactivating, but it's meta directing. So, but the important thing is, this can come from just having this and treating it with H+. You got to be careful. This is known to be an activating group. If it's acidic, though, this group may be existing like this, and may be actually a meta-directing or a deactivating group. Now, this can actually vary. It's like you can be weakly acidic, and it'll still sort of maintain this. It all depends on the equilibrium here, and some very practical things. If it becomes too acidic, and it's primarily existing like this, you actually start getting meta reactions and deactivation. All right? Or Lewis acid, because you can do this with proton acid or Lewis acid, such as metal ions. Okay, it doesn't have to be H+, it could be maybe zinc+. Because any cation is going to be attracted to this lone pair and form a either a bond or a complex, we call it. Okay, so realize that we can turn the activating amino group into actually a deactivated ammonium group. Okay, directing effects. We did this page before. We looked at resonance structures. Try to explain the directing effects. And the directing effects can be additive. Just like we added them up on the sulfanilamide, and they were reinforcing. We'll see that. Reinforced, here's another reinforced direction. What's the name of this compound? There's actually two common names there.
Yeah, it's totally.
Anybody want to propose a name for this?
Is it? Wait.
What common names do you see?
Benzoic acid.
Benzoic acid and also
Toluene.
toluene. Two common names. All right? Well, you'd have to know which to go with, and we don't know that. I would not give you this name. But what I'm telling you is, when you have such, you have to have, okay, which group takes priority? And this would be advanced nomenclature. I know that the benzoic acid is going to take priority. It's going to be named as a benzoic acid. This would be called, thus it would be called what? 4-methyl benzoic acid, or paramethyl benzoic acid. Name it as a benzoic acid with a methyl substituent. Okay? And again, I wouldn't expect you to know that because I wouldn't expect you to determine between which common name takes priority. All right? Benzoic acid is sort of the king of functional groups. The more oxidized the functional group, the more precedence benzoic acid is typically the king. Okay, if we, what are we doing here? Chlorination? Chlorine with a Lewis acid? Yeah? Okay. Where's the chlorine going to go? Well, what do we have here? Ortho-para director? Okay. A lot like sulfanilamide was. That's blocked, so we're looking, this is going to direct ortho. What type of director is this?
Meta.
Meta. It's going to direct where?
Same spot.
Same spot. Reinforced direction. And there's your predicted major product. All right. What about opposing direction? When we have conflicting direction. The answer is the strongest electron donator directs. Because ultimately it will stabilize the intermediate best. An example. Somebody name this compound. That's very doable. What's the name of that compound?
Para-ethyl anisole.
Yes. 4-ethyl anisole. What if we sulfonate this compound? Okay, what type of director is this? Ortho-para. How about this?
Ortho-para.
Also ortho-para. So this is directing here, and this is directing here.
The one with
So where's it going to go?
the one with the lone pair, or group 1.
Well, what did we say? Strongest electron donator directs. Which one's the strongest donator or activator?
That
This is group 1 because it has a lone pair, and this is what?
group
Group 2.
That's group 2. This can donate by resonance. This can only donate by induction. The resonance is a stronger effect. You're only going to get the resonance if the cation falls in certain places. Those places occur when the reaction goes ortho or para. It's going to go ortho to the strongest. And so the major product we would show there, the ortho to the methoxy, not ortho to the ethyl. So it's actually opposing direction, but the strongest activator directs. All right? And you can do resonance structures here. If we do the reaction that way, that means that this is going to have to react here and leave cation here. And then resonance, the cation can move to here, or we can show it here. Then we can show it here. And then we can do resonance structure. But if we do the reaction, you should do that too. If you do the reaction and the group's added here, the cation would fall there, and there, and there. It would never fall here, and you would never get the good resonance structure. And so that would not be as good of a pathway. Okay. There we had a clear winner. Okay? A, clear winner. B, not a clear winner. What if we have this compound? I'm not sure which, we got two common names. We got phenol, we got anisole. I'm not sure which would take precedence here, so let's don't even try to name that. I feel like it would be a phenol. I feel like it's paramethoxyphenol, but, all right. A lot of these actually have some common names. Remember glycol? Showed before, used to make guaifenesin. If the methoxy is actually ortho, it's actually called glycol. Common name. Okay, sulfonation question?
I was thinking, wouldn't methoxy take precedence because you meet induction and resonance there?
No, I'm talking about nomenclature.
Oh, my bad.
Okay, in terms of precedence, which would take precedence?
I was thinking methoxy because they could also have induction from the methyl.
That's not a bad argument, but it's really not connected to the ring.
Okay.
It's possible. Resonance, you are going to show a plus on the oxygen, And then the methyl can maybe stabilize that, so it's a reasonable argument. But it's much closer than above. And they're both ortho-pair directors, so this directs ortho, this one directs ortho. It's conflicting. And it's not as clear here. For us, if they're both group 1, now I showed you the OH and the O ester, and you could maybe make an argument. Perhaps. But it's more likely if you do this reaction or look up what has been done before, you're probably going to get mixtures, more prone to get mixtures here, because it's not a clear winner. Okay? Not a clear winner. They're both group 1. And in the end, that's going to be a reaction that it's going to be tough to get a pure product. And when you do get a pure product, if you can purify these, separate them, the yield is going to be kind of low. All right? It's not a chemoselective reaction. All right? Important word. Not chemoselective. That's a broader term, but before we viewed it's not regioselective. Okay? Now, we don't have any stereochemistry here, the difference between the two regioisomers. Before we may have said it's not stereoselective, and it gives maybe racemic mixture. Well, we don't have stereochemistry here, we have regio, but it's not chemoselective. That's a more general term where you're just not getting any selectivity in your reaction. Let's look at some others here. Example. We got this compound, we're trying to brominate it, bromine Lewis acid. Where's it going to go? I've already shown you the product. What do we have here?
Or group 3 and a group 4.
Ortho-pair director, meta director. So this directs where?
Ortho.
There.
Ortho. Got two different ortho positions in para, which is open. And this directs where?
Meta.
Meta, which is here. That one's blocked. So we got 4 different positions. Well, kind of course, maybe of course, but we got 4 open positions. Which one's going to direct? Why the chlorine?
It can donate an electron pair.
Because it's the strongest. It's the strongest. What do we call it? Strongest what?
Electron donate.
Strongest activator? Well, chlorine's not really an activator. In this case, we can say it's the least strongest deactivator. Okay? 1, 2, 3, and 4. This is group 4. This is group 3. Group 3 is actually more donating than group 4, even though group 3 is a net withdrawer, deactivated. Okay? Basically, in order of the groups, group 3 is going to direct before group 4 directs. Any ortho-pair director is going to direct before a meta-director, because any ortho-pair director is more activating than the meta. The meta is the least activating. It's the most deactivating. Okay? So where's it going to go? If we get rid of that, all 3 are likely. Got 3 positions that can go. Ortho to the chlorine or pair to the chlorine. Of the 3, all 3 major products, this is going to be a tough reaction to get a pure product out of.
Would the bromine want to sit pair to the chlorine though?
Why pair?
Because less sterics.
Well, let's look at sterics, because pair to the chlorine is still next to this group. Ortho to the chlorine is next to the chlorine. Is there any one that's sort of bad?
The first
Maybe
one.
the first one?
The first one. It's more sterics to get this group to come in between these. Here I come, I'm going to, this group is coming up. Here I come, up. The approach is, so it may be that this might be the least. But you still may get predominantly a mixture of the other 2. Because they're both Again, if you look at resonance structures, all this is based on those resonance structures last time. All three products, the intermediate will have a cation stabilized by resonance from the chlorine. All right? So we're under B, not a clear winner. Certainly not a clear winner there. Okay? How about the next one? This is vanillin. Okay? If you eat vanilla wafers and look at the back of the box, it'll say vanillin. Okay? Basically synthetic vanilla. All right? Natural vanilla, from the vanilla bean or whatever, it's got this molecule, but the OH is connected to a carbohydrate. All right? And then in the body, that glycosidic bond can be cleaved to generate this. Okay? So that is in natural vanilla, but it's just connected to a carbohydrate. In vanillin, it's not even connected. They just give you the straight stuff. Of course, in natural vanilla, you may have some other flavoring components as well. Makes it a richer flavor. Where this is going to be sort of just, one molecule, less of a flavor profile. So some people can say, yeah, that's fake vanilla, this is the good stuff. Okay. Yeah. All right, so that's vanillin. We got three groups. So obviously we're trying to brominate. What product are we going to get? Somebody got the products? The bromine is going to be where? Describe the position.
Ortho to the OH.
Got this aldehyde, right? Got this methoxy and this ether. Got the phenol OH.
And then ortho to the OH.
Lacey? Where's the bromine going to go? Where are you going to have the bromine? We're doing bromination. I assume, we're always going to kind of assume we're just doing a monobromination, a mononitration, unless there's reason to say we're going to die. But usually we're, okay? Anything? I would say as well, yes. I would say this is going to be our predicted product. What type of director is this?
A meta.
Meta. How about these? Ortho-para, ortho-para. What's going to direct? Certainly not the meta. Strongest activator directs. Ortho-para, that means it's going to direct where? The methoxy here, ortho and para. How about this? Where does it direct?
Just ortho.
Ortho and para. Para is blocked. Well, this is blocked too. So we got these, and this is blocked. So really, we got the three that are open. And okay, but which one? These are both group 1. How can we decide here? How did you decide, Lacey? Because this is para to the methoxy, and that's directing here. This is directing here. This is perhaps a larger group than that. Maybe sterics, perhaps, yeah, a little bit. Now, we ignored this group. But what if we don't ignore it? Where would it direct?
Meta.
Meta. Here. And that, to me, gives the answer. Because it still is going to influence. Because still, you got cations here. And you still would rather not have a cation fall there because it's going to be right next to that electron core. And if the reaction goes meta, the cation then does not fall there. So I would look at that group as to help decide between as a third thing to look at. And to me, that's why That's why that's the predicted product. But this is like a wash, conflict. Let that group decide. Let it have a chance because, okay, you get that? Down here. Now this is two different rings. First question, which ring is more reactive towards an EAS? Which one's more activated?
Left.
Left one.
The one with the methoxy group. This ring is more activated, so we're probably going to nitrate in this ring. Where at in this ring? What's on this ring? What type of director is this? Ortho-para. What's on this ring? Another ring. What type of director is this ring? That's a pi bond.
Ortho-para.
It is ortho-para. What group of my group?
2.
It's a group 2, 2A. It's going to be, the cation can be stabilized by resonance from the pi bond. So it's also ortho-para. So this is directing ortho, that's directing ortho. Which one's going to win out?
The group 1.
Group 1, stronger activated. Because you'd rather stabilize the cation by resonance from a lone pair. That's going to be more stabilization than resonance from a pi bond. And so I'm just going to draw the product here. You're going to get nitro group right there. That's going to be predicted as the major product here. Consider fluorine. Fluorine. The rings are the same. What's on this ring here? What type of groups? That's bonded and this is bonded. That's an sp3 carbon. What type of director is that?
Two.
Two.
Group 2, ortho-para. Well, this carbon, okay, it's a little pulled this way, but it's a bond to each of these. Okay? This is going to be resonance. Okay? The pi bond conjugated with that. All right? It's also ortho-para. Now, ortho-para from this group is going to be ortho or para. Ortho-para to this group is going to be ortho or para. Now, when you nitrate this, you get 2 nitro. This being 1, this being 2. You end up with the nitro here. It's going ortho-para to this group. This is the group that's directing. Now, they're both group 2 for me, but this is more than just one alkene conjugated. It's a lot of alkenes conjugated. If you do the reaction here, you're going to get cation here, and you can do lots of resonance into this ring. Very stabilizing the cation. If you do reaction here or here, all you're going to get is cation here, and you're just going to have to just say induction, and that's all you can do. In this case, being able to use the other ring for resonance is much more powerful. And that's why this goes here or here. Now, why does it go 2 and not? This is actually the 4 position, because nitro here is not the same as there. It doesn't look like it, but this H here, and there may be something else going on. There's a little sterics here from this H. This is not drawn right. I think these rings are actually a little bit sort of, okay? So this is, if you make these bonds longer, these rings then come up a little bit. And this H starts to point more towards this region. All right? If you look at the discussion of this H will be talked about a little bit of how it can block a little bit. There's a little bit else going on that makes it favor this. But also, how do you know when you nitrated fluorine last week that you didn't get any product here? Maybe you had 5 or 10%. And when you recrystallize, maybe that just comes out for some reason. Because unless you get 100%, you don't know what the other percent was. What was your yield of your nitrate? You haven't calculated it yet. Maybe you end up with 50%. Or what was the other 50%? Maybe the other was this isomer, and for some reason it stayed dissolved in the recrystallization. I don't know. Or maybe it wasn't poured much at all, and what you did is you just lost some of this in the recrystallization. In the end, think about the directing effects for the fluorine, and it's all kind of bonded back through here, but this is really just one ring connected to another, just like this. The only difference is we didn't have these connected. Now it's fluorine. If you just add that, right? Now it looks like fluorine. That's the only difference. Okay. Now that we looked at directing effects, we need to look at, go back to reactions. Reactions. By the way, on the warm-up page here, it's asking you to think about where the chlorine is going to go. All right? Take a look at that. We can go back to here, and what we've covered there, we now need to look at these two reactions. Putting on carbon groups, either as a straight plain carbon, or as a carbonyl. Okay? I think this is back over to our white handout, EAS handout. No, we have a blue handout, right?
Yeah, the fetal craft calculation.
Yes, blue. But, question? Yes. But in this discussion of this reaction, we're going to have to talk about directing effects. Also, but I think more importantly, activation, deactivation effects. So we first have to cover that before we move on to these reactions. Okay, Friedel-Crafts. Friedels and Crafts. You may have heard of Laurel and Hardy and those guys. Simon and Garfunkel. But have you heard of Friedels and Crafts? Okay. These two, they came up with alkylation. Putting an alkyl group on benzene. In this case, like an isopropyl. It's just an alkane group, right? Alkyl. Not a nitro, not a bromo, but an alkyl. In this reaction, the electrophile is going to be our old friend, the carbocation. And we've made carbocations lots before, right? Well, here's the take home. If you can generate a carbocation, the ring will react with it and you can get this chemistry. So we had to recall and remember how to make carbocations. A very powerful thing about this is early on in organic chemistry, it was easier to make bonds to nitrogens and halogens and stuff. That was easier. Okay. What was more difficult way back when is to make carbon-carbon bonds. With this reaction, we're making a carbon-carbon bond. So it was very powerful when it was developed to build larger and larger carbon bonded compounds. This reaction was actually first described in 1877. Sort of the time frame. Where at that point, organic chemistry had been sort of pumping along for a good 50 years. All right. Mechanism. We do have our own Lewis acid, aluminum trichloride, which we use for chlorination. All right. And in that mechanism, the chlorine complex with the aluminum. Well, they can do it here as well. Mechanistically, this lone pair adds some chlorine. And we get chlorine's now minus, aluminum's now minus, and this chlorine is now plus. And at this point, this chlorine is like, hey, I don't want to be plus. It can take its electrons back, and you can go backwards maybe, okay? And this can be in equilibrium. But something else could also happen. It could take the electrons here. Chlorine's like, okay, carbon, I love you, but I need my electrons. And if we do that, what do we generate? We're going to make, I'll come this way, we're going to make a carbocation plus, now this is, I could draw this out, a lot of times you may just see this drawn as AlCl4 minus. Basically, aluminum is bonded to 4 chlorines. Aluminum is minus. We may need to show this out at some point. But get carbocation. Now, with halogens, you know, how do you make oxygen a better leaving group? Typically protonated with proton acid. You typically do not protonate a halogen. Instead, very often the halogens are made positive by complexing to a Lewis acid. In organic 1, remember we use silver ion as a little bit. It's very common to use these other Lewis acids like aluminum trichloride or FeBr3, same as with the halogens, to do this. Complexing with a Lewis acid. Definition of Lewis acid? Accepts an electron pair. Isn't that the definition, right? It's accepting the lone pair from chlorine. Because, in this case, aluminum has an empty p orbital. The aluminum is sp2 with an empty p orbital. All right? Standard hybridization. It's only got 3 bonds. And the aluminum there is, all right, aluminum. Important thing is, okay, structural. Does the aluminum have a lone pair?
No.
Group 3, boron and aluminum, very similar. No lone pair. No octet. 3 regions around the aluminum, we expect sp2. sp2 is this with the p orbital. What type of bonds do you see? Sigma bond to chlorine, sigma bond to chlorine, sigma bond to chlorine. And an empty p orbital. The lone pair of the chlorine is filling into that empty p orbital. Okay? And now the aluminum has an octet, because if you draw a 4th aluminum there, now we have an octet, 2, 4, 6, 8. It has achieved an octet, but now it's minus though. Because now it has, if you do a formal charge calculation, it's got minus. Remember, you can't make aluminum happy. It either doesn't have an octet, or it's charged. But this chemistry can go back and forth. It can be in equilibrium. We can generate carbocation. Now this can attack the carbocation. And we can pull down like this. and that's going to give a mechanism for attack here. We don't have a directing here. There is an H there. We generate cation here, right? Resonance stabilization. But then how do we get final product? Very similar to before when we did halogenation. Chlorine can, aluminum's like, hey, I love you, chlorine, but you gotta go. Chlorine's like, okay, I'll go in my electrons and I'll go take this H. These electrons can move in here, and what does all this give? Give that, and we generate HCl, right? But we also regenerate what?
Benzoic acid.
We also regenerate our catalyst.
Yeah, so is it acceptable to draw the arrow going from the bond between the aluminum and the chlorine onto the chlorine and a lone pair of the chlorine going to the H?
You could do that.
Okay, it's more big.
That arrow movement gives you what you get. Yeah, the true, it's like, okay, one electron's here. Is it this a pair that's bonding at this point, or is it that, which electrons end up adding here? It could be as you described. I mean, at that point, it's probably very hard to tell. A lot of times you just see it as I'm doing it in books. But yeah, you're right out, right there. Okay, does this look pretty straightforward? The main thing here is generating the carbocation. And that's the same old mechanism, our old VAS mechanism. Importantly though, have you ever generated carbocations any other way?
Yes.
Could we use an alcohol here? If you had an alcohol, could you generate a carbocation?
Mhm.
Yes.
Yeah. What about an alkene? Have you ever made carbocations from alkenes?
Yes.
Yeah, the first reaction we ever looked at in Organic 1 was this reacting with H+. And where are you going to make cation, left or right?
Right.
Right.
Correct. This attacks to give what? Yeah, right? A new H here? The same exact cation right here. You can make the same product by reacting with this alkene and an H+ source. It just goes back to how do you generate carbocations? The most common for the Friedel-Crafts alkylation, that's what it's called when you alkylate by making carbocation. The most common is a halide and Lewis acid. But you can do it other ways. Now with alcohols, you can just use proton acid, as shown below. Okay? Now there's a mechanism here. I'm just showing you a Lyme reaction, right? To make R+, that's what we did right here. It's also very common in the more advanced to use a Lewis acid, and BF3 is often used with alcohols. Boron's the same exact chemistry and structure as aluminum. Okay? And so the alcohol complexes with the boron. Boron's now minus. The oxygen is now positive.
If you have a primary alcohol and you've protonated it, would it follow more of an SN2 nature instead of forming that carbocation?
That is one problem. Typically you need a carbocation, and primary alcohols are not going to react as easy. We'll look up there. But when this alcohol now leaves, this becomes BF3OH minus. The boron is still minus. I'm just showing you that BF3 is a common Lewis acid. It is used with alcohol sometimes. where you should already know the proton acid. Does it show alkenes below?
Yes.
Yes, the alkenes shown below. Another way to make carbocations, yeah, from alkenes. Okay, up above, this reaction works with primary, secondary, tertiary halides. It's going back up with the halides. Primary, tertiary, secondary halides. The problem is with primary, I would almost rather tell you it does not work with primary, because primary cations are hard to form. But it often does work with primary, and that's sort of like, okay, what's going on here? Is it really a carbocation, or is it more of attacking something more like an SN2? And so I don't really want to get into that. Chlorine, though, is most common. Okay? Ultimately, you don't care what halogen is there because the halogen's gone in the end. Chlorine's the most common because it's just most common and cheapest, etc. You don't really need bromine or iodine. It's not really a better leaving group. Once you make that chlorine positive, it will readily leave. Now, the chlorine has to be on an sp3 carbon. Okay? You're not going to do this reaction with the halide on an sp2 carbon. Okay? I'm talking about the halide part, the part that gives the cation. These are not going to give cations because you're not going to make a cation on a originally sp2 carbon. You're only going to make cations on what was originally an sp3 carbon. You got to be careful about what I'm telling you here. You can have a chlorine on this ring. For example, we could take this. You could do this with chlorobenzene. But see, you got to understand that where we're going to make cation, here, is the chemistry going to take place here in this chlorine leave or here? Here, the sp3 carbon. You're never going to make cation here. So this is just ignored. But that's just a reactant. The chlorine will still be here. But what type of dry crystal chlorine? Orthopara, because now we have different positions. And so we would get, this new group would be ortho or para. So the chlorine would be here, para, but then you would also get, I'll draw the chlorine in the same place. Well, that's ortho. And so that would be the outcome if we had the chlorine there. We'd be doing a Friedel-Crafts alkylation, and we would get orthopara.
The aluminum cannot interact with that chlorine at all.
Less likely to. One reason, this lone pair is busy doing resonance. And so the lone pairs here are less reactive towards this. Here's the other thing. Even if it did, and we showed it complexed, what are you going to do now? Because remember, what we said is, this is not going to leave and make cation. And so it's like,
Well, like when you have the more positive nitrogen, it was a different kind of director, so if you have a more positive chlorine, would it have to be a different director?
you're asking good questions.
Okay.
I'm looking at the clock. Ask again. I mean, you're getting into, here's the main thing here. It ain't going to make a cation, so what's it going to do? Remember the equilibrium I showed? This can just come back and you can go back. And that's what's going to happen. It's just not going to lead to anything. But over here, complexing over here will lead to cation, and then you can get reaction, and then you're done, and you can't go back. Okay? So good. It was a good question because we see this reaction here can lead to cation, a reaction here is not going to lead to cation. And that's what I was trying to tell you right down there on that line. Okay, so we'll pick up here with problems, limits and problems. We need to pick up the pace in this blue sheet here. Have a good day, guys. See some of you in lab.